Good morning. So, today we will start millimeter wave active devices. Now, different applications, they need different types of requirements. For example, one satellite, let us say a geostationary satellite, it is 36,000 kilometer above Earth's surface. So, obviously it will need very high power to communicate. Now, mobile phone, it needs maybe a few milliwatt, that should be sufficient, but for mobile base stations it is a few watt. So, different applications have different types of requirements. Now, for any millimeter wave systems we need millimeter wave sources, and for any amplifier design we also need different types of amplifiers, power amplifiers, low noise amplifiers, oscillators, switches. So, all involved active devices. So, we will see different types of popular active devices, how they operate, what are their characteristics. So, let us start with the basic chart. So, in general microwave devices, they can be divided into two parts, solid state devices and microwave tube based devices. Again, solid state devices, they can be categorized according to their working principle into four major categories: transistor, field effect transistor, transferred electron devices, and avalanche transit time devices. So, under transistor we have bipolar junction transistor, HPT, tunnel diode, etc. Under field effect transistor we have JFET, MOSFET, MESFET, HEMT, and different types of memory and CCDs. Under transferred electron devices we have GaN diodes, LSA diode, indium phosphide diode, then different other types of diodes. And under avalanche transit time devices we have reed diodes, impaired diodes, trapper diode, buried diode. So, they are categorized according to their working principles. So, among all different types of active devices, popular are HEM, high electron mobility transistor, GaN diode, and the impaired diode. So, in today's discussions we are going to mainly discuss about these popular active devices. And under now microwave tubes we have two different types of tubes, linear beam tubes, or sometimes we call simply O type tubes, and crossed field tubes, or sometimes also called M type tube. So, we are not going to discuss about the tubes. So, mainly we will concentrate on active devices, solid state devices. So, here is one chart which relates the average power versus frequency. So, if we look at this chart where the this comparison we are doing among different types of tubes and different types of solid state devices are being considered here. So, if we look at this chart for any given device, if we increase frequency, maximum available power it decreases. And not only that, the high frequency parts and high power together, these are mainly dominated by the tubes, but the problem with tubes is that they are expensive and bulky. So, we try to avoid them in low cost applications. And now, looking at the different solid state devices, we have again solid state devices based in gallium arsenide technology, gallium nitride technology, and also different examples are a HEMT, BJT. So, again for these solid state devices also power handling capacity it decrease with frequency, increasing frequency. And if you look at this plot, not only that, so gallium nitride usually it provides high power, and gallium arsenide based devices they are used at much higher frequencies. So, the stop curve it belongs to gyrotron. So, but the problem with gyrotron is its size and cost. For example, one gyrotron is shown here, it occupies almost one building. So, you can compare the size with one human beings. Now, microwave power requirements. So, in this chart we see that different applications, they have different types of power requirements and they correspond to different frequency bands. So, right now at millimeter wave frequencies, mainly we have defense and space applications. So, consumer application is very much limited, but with the incoming 5G wireless communication, it might be at millimeter wave frequencies, maybe at 60 gigahertz. So, it is expected that millimeter wave active devices will be used for this type of communications. Now, for solid state devices, gallium nitride based device, it can provide more power compared to other solid state devices, and this is the theoretical limit for gallium nitride based devices, and the second line, it shows the theoretical limit for gallium arsenide devices. So, we will see which parameter determines high frequency operation and its maximum power capacity. Now, here are some more examples of microwave and millimeter wave power sources. So, in most of these applications till now, we have mainly different types of tubes, they are being continuously used. But the disadvantage of these tubes, they are of large size, they are bulky, usually they operate at fixed frequency. So, frequency tunability, it becomes a problem with them, and not only that, they are usually narrowband and it has also spurious spectrum with that. So, for example, in our day to day use, we use microwave oven. Usually it uses a magnetron to generate microwave power at frequency 2.45 gigahertz. Now, in this plot I am showing you the microwave spectrum of one magnetron. So, you can see the peak, it is here around 16.5 gigahertz, but it is associated with many side bands. So, we have many spurious bands. So, the quality of waveform spectrum, it is very poor, and another disadvantage is its high cost. So, then going back to solid state device, so 2 points becomes very important. One is power handling and another one is high frequency operation. Now, if we compare different types of solid state devices which are already available in market. So, here is the chart. So, in the first figure we are showing the output power versus frequency. So, if we increase frequency, maximum output power from the device it decreases, and again we can see that gallium nitride based HEMT, it provides maximum power, whereas gallium arsenide based PHEMT, it provides higher frequency operation. We also have indium phosphide HEMT, it also goes beyond 100 gigahertz. Now, another important parameter is power density, considering component miniaturization. So, how much power is available per square millimeter versus frequency. Again, gallium nitride based devices are the winner, but their frequency is much limited to, let us say, 30 to maximum 40 gigahertz. So, if we want to use them at higher millimeter wave frequencies, then again we have to go for gallium arsenide based devices. But gallium arsenide based devices, it has again one problem compared to silicon based devices, that it consumes much power. So, we will discuss these points later in detail. So, some of the popular devices, their applications and frequency limitations. So, for example, impact device, they are typically used below 300 gigahertz. So, it can cover the whole millimeter wave spectrum starting from 30 to 300 gigahertz. This is, so this frequency, whatever I am mentioning here, it is it represents the popular applications. So, but there are examples where impaired diode has been used above 300 gigahertz, and typical substrate used for impaired diode fabrications are silicon, gallium arsenide, indium phosphide, and they are popular for transmitter amplifiers. So, in a high power amplifiers where we need power amplifier, we can use impaired diode, but they are not much popular as a source, millimeter wave source, because they are associated with phase noise. We will see later. Next is GaN diode, typically used below 180 gigahertz. Substrates gallium arsenide and indium phosphide. It is a very popular millimeter wave source which we use in laboratory experiment in the universities. So, it is popular in local oscillator, also it can be used in transmitter amplifiers. Next, FET and HEMT, typically used below 140 gigahertz, again based on gallium arsenide and indium phosphide, and they are widely used in different types of amplifiers, oscillators, switches, mixers, phase shifters. So, different types of applications. Next is PIN diode, typical frequency below 100 gigahertz, and the materials used for fabrication silicon, gallium arsenide. PIN diode is mainly popular in switching applications, and at millimeter wave frequencies sometimes they are also used as variable resistor. Next, varactor, it can give variable capacitor. So, when we need any tunable components, we can use varactor and we can electronically tune the capacitance of a varactor diode. Typical applications: multipliers, tuning, phase shifters, and different types of modulators. Now, how to choose a material for any given solid state devices? There are several parameters. When we go for millimeter wave frequency applications, so the frequency is so high that signal is changing very fast. So, device it should be narrow enough, so that carriers from left side to right side, it takes minimum time, typically less than the time period of the given signal. So, we characterize it by transit time. So, then the first conclusion is that device size should be small. Whatever carriers we are using here, so carriers velocity should be very high. Now, carriers velocity inside the substrate material, it depends on many parameters. It depends on electric field, it depends on mobility, electron mobility and hole mobility. So, electron mobility or hole mobility, it depends on the type of substrate. So, then depending on our application requirement, we can choose a proper substrate for fabricating the solid state devices. So, here are some examples. Gallium arsenide substrate, they are used because of its high mobility. Silicon substrate, the fabrication procedure, it's very low cost and also high yield. So, for consumer market, silicon substrate is very popular. Gallium nitride substrate, it is mainly used for high power applications, but their high frequency application is limited. Typically, they are used below 30 or 40 gigahertz. Now, we see the characteristics of some popular semiconductor materials. So, we are comparing the band gap energy and mobility at room temperature 300 Kelvin. So, if we look at the silicon, it has a band gap of 1.12 electron volt at room temperature, whereas for gallium arsenide it is 1.43. So, if the band gap value is higher, that means its power handling capacity will be higher. Now, look at the mobility values. So, if I look at the electron mobility, silicon electron mobility is 1600 centimeter square per volt second, whereas for gallium arsenide it is 8500. So, obviously, for gallium arsenide based devices, electron velocity will be much higher under a given electric field, and we can increase FT of the device. We can go for high frequency operation with gallium arsenide based devices. So, some important parameters how we characterize any solid state device. So, for example, output power, or what is the maximum power available from the device, power density, what is the maximum frequency of operation, then power added efficiency. So, these are the mostly well used parameters. So, output power P max, it is proportional to V max multiplied by I max, where V max it represents the breakdown voltage, and I max it depends on how fast we can remove heat from the device, also gate width and length, because the resistance depends on it. Next is power density. Power density is equal to V max multiplied by current density. So, V max is the breakdown voltage, and current density it is limited by band gap and thermal conductivity. Next, high frequency operation, F max it is proportional to Vs by L, where Vs it is the saturated carrier velocity and L is the gate length for a given, let us say, FET, and P max it is proportional to 1 by F square. So, if we increase frequency, it is expected that power will decrease very fast. So, what we seen in previous plots. Next is power added efficiency. So, here what we do, let us say any given solid state device we are using in amplifier applications. So, we will be having RF input power and then the amplified RF output power, and to amplify the signal we have to supply some energy to the device, and this is being done by DC source. Now, how much power it will absorb from the DC source, or what would be the efficiency of the device, we call it the power added efficiency, and it is defined as 100 multiplied by output RF power minus input RF power divided by PDC total DC power what it consumes. So, it depends on many parameters such as wave shape, what is the impedance of the device, then what is the leakage current and power gain of the device. Now, let us start with the first device, bipolar junction transistor. So, bipolar junction transistor also we use in basic electronics lab. It has very similar principle, and only thing is that in whenever we use for low frequency applications, let us say at megahertz frequencies, we do not use the different capacitances offered by the PN junctions. We have 2 PN junctions in BJT, but for high frequency operation we have to consider all these capacitances, and the device also is associated with some inductance because of its leads. We have to also consider the effect of the inductance. So, high frequency model it will be little different than what we used at lower frequencies. So, let us look at one BJT. So, this is a typical BJT used at lower millimeter wave frequencies. So, you can see the base, emitter and collector. So, the bottommost portion it is called the sub collector, an actual collector it sits over the sub collector, and on top of this collector we have a thin layer of base. Gain of the transistor it depends on base width. Thinner is the base, we will have higher gain. So, look at this plot, then this base lead it is connected to this thin layer, and over it we have emitter, and collector its connection is coming from right hand side. So, for high frequency operation we have to decrease the transit time, and if we need to decrease the transit time we have to reduce the base width. Now, looking back to basic operation of BJT, I'll skip the very basic things, only I'm going to discuss the limitation which arises at higher frequencies. So, let us consider one NPN type BJT. Usually NPN type BJT is popular at higher frequencies, since it involves mostly electron and electron mobility is higher compared to hole mobility. So, emitter it will eject electron, and for normal operation we will forward bias the base emitter PN junction, and we will keep the base collector junction in reverse bias condition. So, due to the applied electric field, then electron drifts into base, where we have recombination with the holes available in base, and then rest of the part we have first diffusion and then drift inside the collector. Now, for high frequency operation we have to decrease transit time. So, that means we have to decrease the base width, but if we decrease base width, the problem we will be facing that base resistance will become very high. So, we have to avoid this problem. So, how we can avoid then this high resistance problem? One solution is that we can increase doping inside base, but if we increase doping inside base, then the hole which drifts into electron from base, that part will increase. So, the reverse saturation current will increase. So, then we just can't keep on increasing the doping concentration inside the base. So, that is why conventional BJT it is not used at millimeter wave frequencies. We have some other version which can take care of this reverse saturation current, and this modification is called heterojunction bipolar transistor or HBT, that comes just after this. So, HBT modeling, the first model, this is it shows low signal low frequency model. You can see here we are just considering R pi, the current source GMVBE, and the output resistance R naught, and we are not considering any capacitor. This is the low frequency model. Now, if I go back to device, we have a forward biased PN junction for this base emitter junction. So, forward bias PN junction it is associated with some capacitance. We also have reverse biased base collector junction, it is again associated with some capacitor, and usually reverse biased capacitance is smaller than the forward biased capacitor. So, we have to consider all these capacitor, they are typical values of the order of picofarad at low frequency, that is why we avoid this, but at millimeter wave or even at microwave frequencies we can't avoid their effects. So, then the modified circuit, how it looks here, shown here. So, in addition to the previous one, we have introduced two more capacitors. CBE it represents the base emitter forward bias junction capacitor, and CBC it represents the base collector reverse biased PN junction capacitor, and this is the internal model of BJT. In addition to this, we will have packaging effect, we have external leads. So, we have to add more resistors, capacitors and inductors. For that we will take into account the effect of packaging, effect of the leads. Next, high frequency limitations. So, high frequency limitation it depends on many parameters, and the conditions sometimes we call it Johnson conditions. So, it depends on the following parameters: saturated drift velocity. So, carriers inside the substrate it has some velocity under given electric field. If we keep on increasing electric field value, then this carrier velocity will increase, but finally it will reach a saturation value, after which it can't increase for silicon or germanium or this type of material, semiconductor material. We call that velocity as the saturated velocity Vs. But there are another categories of material, usually group 3, group 5 semiconductor materials like gallium arsenide. So, for this type of materials, after a highest velocity Vs, if we keep on increasing electric field, then Vs decreases. So, we will consider this maximum velocity of carriers Vs, and then next is the dielectric breakdown. Dielectric breakdown, it depends on applied electric field and it is a property of that given dielectric. So, let us call the breakdown electric field is Em. Then maximum current, it is also limited by the base width. So, considering all their effect, if we plot current gain for a BJT, it becomes a function of frequency. So, here in this graph we are showing the plot of HFE, forward current gain, or sometimes we call it beta. So, typically you see at lower frequencies it is fairly constant, but at higher frequencies it decreases, and at a frequency current gain it becomes 1 or unity. We call that frequency Ft of the device. So, it mainly depends on the capacitance values. Now, let us see some parameters which determines its maximum frequency of operation. So, the first one is voltage frequency limitations. So, here Vm is the maximum allowable applied voltage to the device. It is given by Em multiplied by L minimum. So, L minimum is the distance between emitter and collector, and Vm multiplied by Ft, where Ft this is 1 by twice pi tau transit time cutoff frequency, it is equal to Em Vs by twice pi. So, Em, that is the maximum allowable electric field, and Vs, that is the saturated trip velocity. So, Em Vs by twice pi, then we see that it is related to the maximum allowable applied voltage multiplied by Ft. So, if we increase frequency, then maximum allowable applied voltage it decreases. We can also express this quantity Em Vs by twice pi in terms of current frequency, in terms of power frequency. So, simply we have to replace the voltage by the corresponding expression of current and corresponding expression for power. So, it is shown in next slide. So, the current frequency limitation, here Im into Xc multiplied by Ft equal to Em Vs by twice pi, where Im is the maximum current of the device and Xc this is the reactive impedance of the device. So, it depends on Ft and mainly based to collector junction capacitance. Then the power frequency limitation. So, square root of Pm into Xc multiplied by Ft equal to Em Vs by twice pi. We also can define power gain frequency limitation. So, Gm Vth Vm whole square root multiplied by Ft, this is equal to Em Vs by twice pi, where Gm this is the maximum available power gain and Vth this is the thermal voltage. So, it depends on room temperature. So, what we see then, gain of any BJT, it becomes a function of frequency. At higher frequencies we will expect lower gain, and not only that, it also a function of temperature. So, we will take a break, then we will move to next topic, HBT. Thank you.